Okay, we are about to start our monthly Tucson Amateur Astronomy Association meeting. We would like to welcome our people in the room tonight and our people who are on Zoom and who are on Facebook. We're delighted to have you all here. And I'm going to hold the mic a little bit closer. Can you hear better now? Okay, so the sound is going better now. Okay. Thank you. Welcome to our monthly Tucson Amateur Astronomy Association meeting. I'm May Smith. I'm the TAAA president, and we're going to have a very interesting presentation tonight. We're going to ask our people in the room to be as quiet as possible on Zoom because their sound will carry throughout the Zoom communication. So we'll ask that that we have people, be as quiet as possible, and we are having some more people enter who are being enormously sensitive about noise. So thank you so much for that. We do have a guest speaker tonight who's going to give a nice presentation for us, whose name is Dr. Conrad. And we sent out literature several times about him and his background. And so, Dr. Conrad, if you're ready to start, we are ready for you.
Okay, great. Can you hear me okay?
Yes.
Okay, I'm just going to share my screen here and get started then. Okay, hello. Thank you very much for inviting me to give this presentation. Today, I'll be telling you about our observation of Jupiter's volcanic moon Io with a new instrument on LBT called SHARK-VIS. And SHARK-VIS is, we believe, going to be ushering in a new era of planetary imaging. So here's the topics I'm going to cover in the talk. I'll give a little background information about Io. Then I'm sure most of you are familiar with the Large Binocular Telescope, but I'll give a little background about LBT itself, about the adaptive optics system and the upgrade that we recently gave it. And then the topic at hand, this new instrument, SHARK-VIS, and how we used it to observe Io. And then at the end of the talk, I'll talk a little bit about our plans for the future using SHARK-VIS and a new technology that will be coming for doing even more impressive planetary imaging in the future. Okay, just bear with me a second. As often happens with Zoom, I've got things in front of the screen that I need to try and minimize. Great. Okay, so yeah, Io, as you know, is one of the Galilean satellites, one of the first 4 that were discovered by Galileo when he first started using telescopes to look at the heavens. And it's the innermost. It's not huge. It's slightly larger than Earth's moon, coming in around 1,800 kilometers. It was volcanic activity was discovered on Io. This is the discovery image. Spectacularly when the Voyager spacecraft flew by. And for those of you who are old enough, you may remember where you were in 1979 when Voyager made the encounter with Jupiter and Io. I know I certainly do. It was a milestone in planetary science and a really exciting time way back then. Io has hundreds of active volcanoes. But what is powering these volcanoes? You're probably most of you are aware that the source of the heating of the energy that flows to the surface in the way of volcanoes comes from tidal heating, the same effect that we have on Earth here that gives us high and low tides, where when bodies line up, when the Earth and when the sun and the moon line up for a full moon or a new moon, we get extreme tides, deforming the actual shape of the ocean. With Io, it's a little more extreme, and it's actually deforming the rocky makeup of Io, the mantle, and that results in energy in the way of heat, and that lineup is caused by Jupiter with mostly Europa. As you can see in this little animation, the 3 inner moons are in a resonant orbit. So every time Ganymede goes around once, Europa goes around twice, and Io goes around 4 times, making for many opportunities for these bodies to line up and exert a gravitational tug of war and actually distort the mantle of Io and cause this heat. But the details, an active area of study is the details of how that energy is dissipated and transported to Io's surface in the way of volcanoes. So this is a figure from an article that was recently published just 2 months ago by one of the co-authors on our paper, Ashley Davies, volcanologist at JPL, who they used images of Io taken with the Juno spacecraft in the thermal, in the longer wavelengths, and from that they gained a little more understanding of this process by which the heat transfers to the surface. For a while, there's been these 3 leading theories or models of what the mechanism might be. There's the possibility of it being in the deep mantle, or in a shallower region called the asthenosphere, which is near the surface of Io. And then the other one, also a sort of shallow theory, is that there's actually a continuous magma ocean below the surface. And this data analysis shows a preference for the shallower of these 2, either the deep mantle or the asthenosphere. So this is an active area of study and research. And to carry on this research, we need to continue to monitor Io and look for changes on Io, for new eruptions, for new surface plumes. So we do that in the infrared, but it's also very important, equally important, I would say, to do it at visible wavelengths, where you can actually see, so to speak, longer term effects like plume deposits that grow and shrink over time. So these are the ways we've been monitoring Io. We have spacecraft images, which of course get exquisite, wonderful, high spatial resolution images, but they kind of are far and few between. The Voyagers both went by in '79. I should mention that there's never been a spacecraft that actually orbits Io. And it's unlikely that there will be anytime soon because of the intense radiation field there. So all these missions are Jupiter orbiters with flybys of the various moons, and including Io. Galileo was there near the turn of the century from '96 to about 2002. The Juno spacecraft arrived in 2016 and has occasionally imaged Io, and it will continue through around 2025. Hubble Space Telescope is our really only other means to date of monitoring in the visible with high spatial resolution the surface of Io. There's been a lot of ground-based imaging of Io with adaptive optics in the infrared wavelengths, but to date, it's only been Hubble in the visible, and ground-based, Earth-based telescopes that use adaptive optics tend to always, until recently, observe in the infrared, not in visible wavelengths, and I'll explain why in a few slides. So we need to be regularly monitoring, and Hubble Space Telescope has been the way that we've been able to observe in periods when there's not a spacecraft in visiting Io, which is the majority of the time, and going in the future will be even more so. So here's 2 images of Io, one taken from a ground-based telescope and one taken by the Hubble Space Telescope. Which is which, I might ask, and the answer might surprise you, that it's actually this blurrier image on the left is the typical image from the Hubble Space Telescope. And this image on the right, showing much more detail, was the image that we acquired with adaptive optics from LBT on the ground here on Earth. So let's talk about the Large Binocular Telescope. I'm pretty sure most of you are aware of the Large Binocular Telescope, but I'll just give a little bit of review. It's located in eastern Arizona near Emerald Peak on Mount Graham. It consists of two identical 8.4 meter mirrors and this is important, they're on a common mount. So whenever we observe with observe with LBT, just want to double check to make sure my camera's on there. That's great. So whenever we observe with LBT, both of these mirrors, it's a single telescope, they're both pointing at the same neighborhood of the sky. And when we combine the light from both mirrors, the total area is about 110 square meters, which would be the equivalent of a 12-meter telescope. So sometimes we refer to LBT as a 12-meter telescope when we're just using it as a light bucket, where we're trying to go faint and observe objects. But what's also important, and I'll get more into this at the end of the talk, is that the edge-to-edge distance between these two mirrors is 23 meters. More about that later. So I'm going to talk a little bit about adaptive optics now. Maybe I'll just, maybe I'll ask for a quick show of hands on Zoom, and maybe you could tell me in the room there, if you could raise your hand on Zoom if you've heard of the term adaptive optics and you have a rough knowledge of how adaptive optics works and why it's important in astronomy.
We have a number of hands in the room.
Okay, great. Okay. Yeah, and they're coming in on the as well on the Zoom session, but not so many. Okay, so I'll spend a little time on this. So adaptive optics, or AO as it's referred to, corrects the blurring effects of the Earth's atmosphere. So often we talk about the light that comes from objects we're going to observe. We talk about its wave front. And that wave front is perfectly smooth as it travels through space, sometimes over great distances, until that last small portion of time when it has to go through the Earth's atmosphere. And sometimes I think of it as like a wrinkled bed sheet. It's basically going through different portions of the atmosphere, which have varying temperature, and that aberrates the wavefront and turns it into from a flat bed sheet to a wrinkled bed sheet. And that has severely limited what detail we can see from the ground until the mid-90s, when adaptive optics started to become a technique for astronomers. So the shape of this aberrated wavefront in our AO system is measured about 1,000 times per second. And that's done by this component down here called the wavefront sensor. So we sense the wavefront, we measure it 1,000 times per second, and then those measurements are converted into commands that form the shape of a deformable mirror. So this is a thin mirror with a lot of actuators behind it that can take on any shape, and the shape we put onto that mirror is the reciprocal, basically, of this distorted wavefront. So wherever there's a peak in the distorted wavefront, there'll be a valley on the mirror, and vice versa. And the result is that the bed sheet comes in wrinkled, and by the time it bounces off this mirror, it's essentially flat again. We've restored it to the flat wavefront that came in, and it's like magic. It's it's like putting on a pair of spectacles where you're seeing a blurry image like this one on the left, and when you turn on the AO, when you close the AO loop, then suddenly you see all this detail just like you do when you put on your glasses. So historically, AO systems have sensed the wavefront using the visible end of the spectrum, and sent the infrared light to whatever the science camera is. And so this is done by means of a dichroic, of an optical element that separates the red light from the visible light. But and one of the reasons that's been done is that it's hard to do get AO correction in the infrared, I'm sorry, in the visible wavelengths. The correction you get is going to be wavelength dependent. So you usually get great correction at the very long thermal infrared, 8 to 10 microns, and you get good correction at 3 to 5 microns, which is the so-called L and M bands. But as you get shorter, it gets harder. You can sort of think of it as the wavelengths are as it gets smaller and smaller, you need a more fine-grained sampling and ability to correct. And so in particular, you need a deformable mirror that is going to have more actuators. And that is been kind of limited by the technology, but there's been breakthroughs to where now we have mirrors with more and more actuators. And it's also doing good AO in the visible depends on, or has been assisted quite a bit by breakthroughs in detector technology, which I'm sure in your group you're familiar with, the new low noise EM CCDs and the CMOS CCDs, which we'll talk a little bit about now. So LBT, Large Binocular Telescope, is unique. It's always been at the forefront of technology. And one of the ways is that instead of having its deformable mirror, which is, I've drawn a circle around it here, down near the instrument. So this, for example, is the workhorse deformable mirror that was on Keck for many years, all the time I was there, and is still in use, down near the instrument. LBT went with what's called adaptive secondary mirrors. So the advantages of an adaptive secondary are that there's several. One is that you're able to correct the light and send it to any of your instruments, whatever focal station around the telescope you're at. And the other primary advantage is that ultimately you're going to have fewer reflective surfaces, fewer warm reflective surfaces. So your thermal background, your ability to observe in the infrared is much more efficient, and your sensitivity in general is more efficient. The downside is they're hard to build and they're hard to maintain, but that's a technology that we've got a handle on now. So LBT has 2 adaptive secondaries, one above each primary mirror. And in order to build an adaptive secondary, because it's almost a meter in width as opposed to something small like this, you have to have a lot of actuators. And that turns out to be the advantage that we need in order to do AO in the visible. So the other thing that's been happening at LBT is we've upgraded this wavefront sensor. So this is, recall the sensor that has to measure the shape of that distorted, aberrated wavefront. It's like a wrinkled bed sheet at 1,000 times per second. So you need an efficient, sensitive detector. And so in this upgrade, which just finished actually the latter part of last year, we replaced the old detector, which was called a CCD39, with one of these new electron multiplying CCDs. And there's a lot of numbers here, but basically we can read this detector out twice as fast as the previous one, even though it has 10 times as many pixels. And most importantly, at 1/10 the noise level. And so this really is a game changer for our adaptive optics system. Okay, and then the last piece in the puzzle is you have to have an instrument that can take advantage of this corrected beam that is provided by the adaptive optics system. And for that, our colleagues in Rome provided SHARK-VIS, which the acronym is not a great one. It's the System for High Contrast and Coronagraphy from R to K at Visual Bands. But anyway, SHARK-VIS is our new instrument, which just commissioned in the middle of last year. And it's has, thanks to this new technology detector, it can, for very bright objects we look at, it can read out 1,000 frames per second. So the observation I'm going to be talking about of EO, we read out at between 100 and 200 times per second. We had 5 to 10 millisecond frame time. So going back in history, the AO systems started showing up in the mid-90s with the PUEO at the Canada, France, Hawaii telescope, 3.6 meter. Yeah, I'm talking about large telescopes now. And then the other large 8 to 10 meter telescopes quickly followed suit with their own AO systems, working with an infrared science channel, as I showed. And then now we have this new population of more higher spatial resolution. So I'm showing the spatial resolution here on the y-axis, measured in milli-arc seconds, 1,000th of an arc second. 1,800 arc seconds is the diameter of the moon or the sun on the sky. So the milli-arc second is a very fine angle, and we measure spatial resolution in angle and milli-arc seconds. So starting around 2013, 2014, we had these first of these visible AO systems, taking advantage of the technology, more actuators in the AO system, advanced visible light detectors, EMCCDs and CMOS. And the most notable two, both in the Southern Hemisphere, were Magellan, right here at the University of Arizona on the 6.5 meter Magellan telescope in Chile. And at the VLT on Paranal, also in Chile, the SPHERE instrument. Now, around this time, shortly after, a few years after, the SHARK-VIS instrument was ready. Pretty much, we'd had a final design review and a Delta design review in 2017, and the final preparations were being made to have a pre-ship review, and then hopefully be shipping it to LBT. And in late 2019, bam, we had COVID. So we had to fast forward 3 or 4 years. A lot of the team started having to work on other projects during COVID, and we had to reassemble everybody, go through the review process again, make sure everything was ready. And then finally, in the middle of last year, SHARK-VIS was installed on the Large Binocular Telescope. And one of the first things we decided to look at was Jupiter's volcanic moon Io. So this is a lot of detail. It's a table from the paper, but the takeaways are that we observed it on 2 occasions, on the eve of Thanksgiving, on November 23rd, and again on January 10th. Now, Io was at its largest, closest at opposition on December 7th, 2023. And you can see for our first observation down here that it was, just over 4 AU. But by the second observation, it had already moved to being, 15% or so further away, and therefore smaller on the sky, getting back down to just about an arc second, which is the typical diameter for EO on the sky. But for that first observation, it was 1¼ arc seconds. The total time we spent on EO and turned into our publication was 45 seconds. But truth be known, it was this is a new instrument, and there was a lot of newness to it. And so the overheads were quite high. There was several, I'd say roughly 3 to 4 hours combined over the 2 nights. 1 or 2 hours each of those 2 nights was spent just in overheads, getting set up, getting the AO just right to take this precious data. So this is sort of the raw images. I mean, they've been frame selected. We took, thousands of frames, as you can see in this column. But with just a simple shift and add and some co-adding and looking at the individual filters we observed in the IR and V bands. These are the images from the November and January observations. And for those of us who had been looking at EO for, commonly, we noticed something was different, right away. This was not a subtle result. There's, I'll say more about it in the future slides, but right around here, we have Pele. By the way, this is Loki over here. And right here on, EO's persistent large lava lake volcano Pele was, it has normally a ring around it, a plume deposit, and there was like a bite of it missing from something that had happened over here at like the 2 o'clock position around this ring. So we were getting, the conditions were not ideal. Theoretically, with SHARK-VIS, we could get down to about 16 milliarcsecond, which would correspond to more like 50 kilometers on EO, but we were getting 24 milliarcsecond roughly on both nights, corrected images, and get resolving features down to a size of 80 kilometers on the surface of EO. So yeah, we noticed this bite taken out of the ring. And so this shows Pele's red ring a little more clearly. This is a mosaic formed of older images, Voyager and Galileo images, so from the 70s and around the turn of the century. Spacecraft are great, but you never get the whole disk. You get great spatial resolution, zoomed way in, but to form the whole disk, you have to make a mosaic. So this mosaic is formed from a wide span of time of images, but it shows some of these, things don't change on the surface of EO that much. And so here you can clearly see this red ring. It dominates the trailing hemisphere of EO and is approximately 1,200 kilometers across. So when we formed, again, there was no extensive post-processing of this data. This is just shift and add and registering the frames and combining the 3 colors. But when we had this combined 3 colored images, this bite out of the red ring, and now we can see that the Pele's ring is red in our data. And well, I should say that this red color, by the way, is an indication that Pele is constantly erupting and replenishing this, because it's believed that this sulfur-rich material that is forming this big deposit would gradually change to a more of a yellowish, sulfur color over months or years, should Pele ever stop replenishing it with fresh material. So we saw this bite even more clearly in our 3-color image, and so we thought, well, when did this happen? Let's go back and see when there was, how was this missed before? And it turns out that even though Juno, had been in orbit around Juno since 2016, it hadn't been spending that much time imaging EO, and when it did, it was more the polar regions, and it had not imaged this area. But we didn't have to go all the way back to Galileo. It turns out that about 8 years after Galileo, in 2007, the New Horizons spacecraft on its way to Pluto-Charon flew by EO and took this high-resolution image. And you can see that in this image, Pele's ring is intact. So we had that data point. We knew that it was sometime more recent than 2007. But we had sort of more to go on than that. When Galileo was encountered at Jupiter and flying by EO, a very similar event took place. And in this case, it was this nearby Patera, Pilon Patera, which had a quite explosive eruption, and in very much the same way as our shark we see in our SHARK-VIS image, but 25 years earlier, took this big bite out of Pele's ring. But as I said, Pele is constantly repairing this ring, replenishing it. And so from the time it was at its peak around 97 to the end of 2000, it had been pretty much completely repaired. And so, there's only so much you can do with a comparison like that, but we might think that the amount of time that this resurfacing event that we detected with SHARK-VIS would be taking place on the order of, lasting 2 or 3 years, as happened before in the event that Galileo observed. So maybe I'll highlight that, you can see that resurfacing events like this are not that uncommon on EO. What is new and exciting about our observation is that we now have this technology, this capability, that from Earth, without having to wait for another spacecraft mission, Juno's going to wrap up in a year or two, and not having to rely on the blurrier images of HST because it has a smaller mirror, we can now regularly monitor and look for these kinds of surface changes on the surface of EO. So we wanted to do our best to be able to go back in time and track down what might have been the explosive event that resulted in this resurfacing that we saw with SHARK-VIS. So we compiled through colleagues that had connections, the co-authors on the paper had connections at other telescopes, and we compiled data from Juno itself, and from which are these P observations in this table. This is a table from our paper. IRTF on Mauna Kea, Keck on Mauna Kea, Gemini North on Mauna Kea. We compiled this list of measurements at lower resolution. Like here's on the right here are some sample images from Keck and Gemini. You can see it's much lower resolution, but sufficient resolution that we're going to be able to see an explosive event and be able to trace it to its approximate location, whether it's at Palan or some other patera. And we saw that there's this, mostly small numbers here, but this big number in gigawatts per micron jumped out. And so we strongly suspect that this resurfacing, this plume deposit that we see in our SHARK-VIS image is the result of a powerful eruption that occurred in August 3 years ago in 2021. So we submitted our paper. We wanted to get it in fast, so we actually submitted it in late January, even though one of our observations was January 10th. We'd mostly been working with the previous observation from November, and we were pretty much ready, and then we added in the January 10th data, and we wanted to get it to press for 2 reasons. One is we were a little worried that Juno would image this area and see what we saw, and it's much better to publish something where you say we saw it first than, yeah, we also saw this. And so we wanted to get it published soon for that reason. It wasn't a subtle discovery, so we didn't have to do a ton of data analysis. It's very clear and visible. And so we got the paper submitted by the end of January. But the other thing is we wanted to be out there in the literature advertising this great new capability on LBT. And but in the months in between February, March, April, this much longer process, it takes huge amounts of computer cycles. And this was work done by our colleagues in Georgia State University and also in Rome. The same team that built the instrument, they have a strong department there doing image processing, post processing, doing what's called deconvolution. So you're probably aware of this deconvolution technique, but it's in very broad terms. You have your image, you use adaptive optics, but you didn't perfectly by any means correct the aberrated wavefront. So you still have some distortion. And one way to measure that distortion is on the same night to observe a star, a point source. And then you get what's called a point spread function, which shows what distortion you're experiencing on that night, broadly on average. And so you can say, okay, well, the real image I want has been convolved by this aberrated point spread function. I know the I've measured this aberrated point spread function, so I can back out to some degree the original information and get the deconvolved, before it was convolved by this aberration. And it's a very exciting technique. You have to be careful. You can get artifacts. You can, produce things that weren't in the original image, but these guys are really good. And we had some, confirmation. It was, for example, the island in the middle of Loki's lava lake showed up in the deconvolved images, which were not was not visible in the more unprocessed images. So yeah, we got these great deconvolved images, and then in the review process, we were able to include this sharper image in our publication. So yeah, we published it, went live on June 4th, and it's available, and I've covered a lot of what's in that paper in this talk. And I really want to acknowledge and thank the co-authors. Fernando was the principal investigator on the SHARK-VIS instrument in Rome, and these two members of his team, Gianluca, was the driving force behind the deconvolution, which I just described. Simone's the science lead for their team. Imka and Ashley, I mentioned Ashley earlier, they're the volcanologists that really understood the science. And so I really want to acknowledge and appreciate their help on this paper. And so now, what's next? We've got this great new capability with SHARK-VIS. And so what are we going to do with it in the area of planetary science and planetary imaging? Well, we'll for sure continue to observe EO. Excuse me. The next opposition's on December 7th. We've got observing proposals in. Hopefully the TAAA will give us time. And then we will continue to observe it, looking for changes like we saw every 13 months. Juno's got a little bit of time left in its mission. And since we have ties with Juno through Ashley, we're going to hope to schedule some sort of, if the Mount Graham weather cooperates, a simultaneous observation with Juno. We've already started to look at asteroids, Electra with its 3 moons, Pallas with its tantalizing hint of a bright brine feature like we see on Ceres at Okator. Dark spots on Neptune and Uranus outer ring. These are both projects that Imke de Potter's been working on and hopes to use for SHARK-VIS. Okay, so that's what we're planning to do with SHARK-VIS. But technology-wise, what's the next big step? Is there another leap, or have we gone as far as we can in spatial resolution at visible wavelengths at LBT? Well, to answer that question, I want to review an observation of EO that I was involved in 11 years ago when LBT observed EO, but at longer wavelengths. So as I'll get to in a later slide, the spatial resolution is directly dependent on what wavelength you observe. So when we're observing in the visible, like 0.5 to 0.8 microns, then we're getting basically 10 times better spatial resolution than you do at 4.8 microns. But at 4.8 microns, which is the so-called M band, you get thermal information. You can measure heat, you can measure the temperature. And in this observation, we were actually able to resolve that lava lake around Loki, which I showed in earlier slides. We were actually able to pick out 2 distinct thermal emission sources with a little separation between the 2 in the lake, and that led to analysis of how that lake is being replenished. And we did this not by using a single side of one of the 8.4 mirrors of LBT as we did with SHARK-VIS. We used the full both mirrors, but not in that 12-meter mirror where we're just adding the light from the 2. We actually phased the 2 mirrors, which is commonly done. And in this way, we used LBT sort of like a 23-meter telescope. So there's a common focus. SHARK-VIS is sort of here, and other instruments are, around each individual telescope. Many of the instruments come in pairs, so there's an identical one on each side, and that's how you can combine the light to do the 12-meter telescope mode. But this one instrument in the middle, called LBTI, the LBT interferometer, accepts light from both telescopes. And what you get, here's a figure from the paper we wrote about this M-band imaging of Loki Lake. But we looked at, this is Loki here, this bright spot. But when you look down here at one of the point source volcanoes on Io, you see this fringe pattern. So the resolution that you get across the central fringe in this pattern is 3 times the resolution of the 8-meter telescope. You're getting the resolution of the full 23-meter telescope. So in this observation, it was just 1 hour's worth of data collection on Christmas Eve, 2013. And this is important. We observed it at a time when the sky was rotating, when Jupiter itself, the region of the sky around Jupiter, was rotating rapidly with respect to the LBT, which is an Altaaz telescope, which I'm sure you're familiar. Without a rotator, then the sky will rotate, the field will rotate. And so if you don't have some sort of derotator mechanism. So this is often done, you actually take advantage of this mode where the sky rotation is an advantage for you. And so we have these fringes have rotated across. And in a way, by using this sky rotation, you're sort of filling in, as the sky rotates, the 2 8.4-meter mirrors are filling in the full area of a 23-meter telescope. So you have to take several observations, but with that restriction, you have a 23-meter telescope. Using what are now sort of standard Lucy Richardson techniques to standard in the interferometry world, to combine, we were able to combine these 7 images and find, identify many volcanoes, discovered a few new ones, and this is all done now. This is a complete image of Io at 23-meter resolution. Well, could we do the same thing in the visible? So again, the spatial resolution that you're going to achieve fundamentally depends on 2 things: the wavelength, lambda here in this equation, and your entrance aperture, the diameter of the primary mirror, 8.4 meters, or in this case, 23 meters in width. So if we move this wavelength from the 4.8 microns that we used 11 years ago to observe Io, if we can now do it at 0.5, 0.8 microns in the visible, then now we're increasing the spatial resolution by a factor of 6 over those observations, by a factor of 3 over what we did with SHARK-VIS, and we could actually get down below 10 milliarc-second imaging, which would be the holy grail. That's the best we could ever do with LBT, but it's possible, and we're making plans to do this. So to give you a feel for the kind of resolution we would achieve, I did a simple simulation in which here's one of the images I showed earlier. This is the I-band image of Io. Here I took the spacecraft very high resolution image of Io, and I convolved it with effectively the PSF of an 8.4 meter telescope, achieving 27 milliarc-second. It's called an Airy pattern. And I got this image, and I said, okay, well, that's roughly this showing I'm getting the same resolution. My simulation roughly works. It's the real data. So now I'm going to decrease the size of that Airy pattern. I'm going to go with a 9 milliarc-second pattern, which is the spatial resolution that we would get with this LBTI interferometer visible extension. And you can see we would just get this exquisite detail. And that's our holy grail, and that's what we're hoping to achieve in the years to come. When we do that, and I do believe we will do it, this will be the beginning of a third sort of population of high spatial angular resolution, where we're really getting down low on this scale of getting down to 8 to 10 milliarcseconds. And the only other entries in this new population of high spatial angular resolution will be the ELT, the GMT, the European ELT, and possibly the TMT. So in conclusion, we have a new instrument on LBT, SHARK-VIS. We used it to obtain the highest resolution images of EO ever acquired from a ground-based telescope. And these images revealed a plume deposit that overlaid Pele's persistent red ring. SHARK-VIS ushers in a new era of planetary imaging from the ground. And the LIVE project would triple the resolution of SHARK-VIS and establish LBT as the first of the ELT. And with that, I'll take questions. I'll stop my sharing.
Okay, great. Thank you so much, Dr. Conrad. We're going to start with questions in the room to give our people on Zoom and on Facebook more time to type in their questions. So I will begin in the room. And question 1.
Wow, that was really impressive. Wow. A question and an idea here. The question would be that the red ring around Pele is from sulfur, but the Palin ring that was overlapping it looked white in this image.
Yeah.
What would be the not sulfur, or what would it be?
Yeah, I have to tread lightly here because I'm not the volcanologist on the team, but yeah, from the paper, I think the white was actually frost, SO frost, and the dark it sort of I'll share the screen again and pop up the image. Let's see, I think the best one is probably this. Yeah, so this or maybe one of these ones where I did the, yeah. So yeah, the white material I believe is frost, and the darker material I'm not super sure, but it's all silicate based. I mean sulfur based, but I think this is SO frost, and I believe that's mentioned in the paper. So I refer you to the paper for more detail on that.
Oh, it's a different version of sulfur.
Yeah.
And so here is an idea or request or something. I'm guessing that with your new system, one of the solar system items that you could look at is the moon Nereid around Neptune. And it's a still nagging open question as to how out of round, or even whether there's a moon around Nereid.
Oh.
Your resolution in a big telescope. Hey, why don't you head off to take a quick peek at Nereid, see what you can find.
Okay, yeah, no, there's I know that IMCA in particular there's other intriguing things about Neptune. So yeah, we definitely hope to point SHARK-VIS at Neptune in the coming years.
Okay, we have another question.
Hey, Doug. I didn't know Doug was on.
Well,
hey, how are you doing?
pretty good. Hey,
Yeah.
this,
I can barely hear you.
optics. Can you hear me now? Can you hear me now?
Yeah, I do.
Okay. That adaptive optics technique there is unprecedented and appears to be unprecedented in any Earth-based telescope. I was wondering if this would lend itself to stellar astronomy and being able to image true disks of certain stars, most notably Betelgeuse and Antares, 2 red giants, because already there have been true disks that have been taken of those stars, but they were very primitive, and they wouldn't have gotten there within the theoretical limits of some of the resolution limits of some of the largest telescopes. But this I would imagine would be able to lend itself to that kind of a study as well as to any uh, solar system objects and especially asteroids. And I can see how that'll lend itself to that. But I would think it would equally lend itself to the study of certain stars.
Yeah, so I mean, so stellar surfaces, like seeing storms and stuff on Betelgeuse, has been talked about. That probably is more the realm of that future, super high spatial resolution, getting down to the 8 or 10 milliarc seconds. However, the driving science case for SHARK-VIS is not planetary science. This planetary science result is great, and EO makes a great, visible demonstration of the capability. But the driving science case and what SHARK-VIS is used for most of the time are planet-forming regions around young stars, disks, especially in the Taurus Auriga area, where there's a lot of planet formation going on, and looking for H alpha, which is an indicator of planets forming through accretion. And again, not my field, but I'm aware of this, and I know that that's SHARK-VIS is the driving science is looking at stars and in particular planet forming circumstellar disks and planets forming in those disks.
Also, there are those in the Orion Nebula. There are planet forming. They're like pockets. There where it's just where it's the gas is condensing and the star is actually forming right before our telescopes. I guess.
Star formation, right? But this is planet formation in exoplanets being formed in circumstellar disks.
Okay.
Is one of the driving forces behind SHARK-VIS.
Oh yeah, and I guess it would lend itself to that. Well, that's really exciting. I have to, and it's almost going to put space telescopes out of. They're going to be
not true. Yeah, it's not. It's all complementary. It's
okay.
Yeah.
Thanks.
Sure.
Okay, another question? Do we have another question in the room? Okay, I don't seem to have a hand. So Terry, do you want to start on questions? We have Terry Lappin, who's doing all of our technology here tonight. So, okay. So apparently we have David on Facebook. And so David, do you have some questions?
No questions on Facebook, but several likes and a hello.
Okay. So Jim, do you have any questions from your group? So there's no questions. Okay, so Terry's.
Yes, on Zoom, there's some questions.
Jim, do you want me to do the questions here?
I can read them
Yeah,
also.
why don't you?
Okay. All right. For those out in Facebook land and such, let's see, there's some thanks for the presentations. And let's see, from Alex, he says, given this greater resolution and the relative motions between the Earth and EO, could stereoscopic images be generated?
Gosh, I don't really have a good answer for that. I don't know of that being proposed. Yeah, I have to defer. I'm not sure if that's possible or not. Yeah, it's important to note that the Large Binocular Telescope consists of two mirrors, but it does not work like a pair of binoculars at all. Yeah, that's for sure. But yeah, I don't have a good answer for that. I don't believe that that's possible. But let me think about that some more and ask my colleagues, and I can contact you. Yeah.
From Doug, AI is making large impacts for helping achieve high resolution for amateur telescopes using
Interactive, I think. Yeah.
Okay, that's what it is. Lucy Richardson gradient descent approach. Did the team in Rome use AI for their approach, or was it something else? Can you share any details?
That's the first I've heard about AI being used, but that's fascinating. The details, I'm really not an expert on this deconvolution, but I can just, as I understand it, and it was words in the slide, and I basically just pulled them out of the paper from Gianluca. But I think the innovation of this Kraken is that it somehow makes use of the information in the frame-to-frame changes in the point spread function. So that's not the point spread function, obviously, that was measured to the star, but it's somehow, I guess, estimating the point spread function, maybe by using some of the unresolved detail on EO's surface, and somehow looking at the frame-to-frame changes in the PSF to then even to make a even more detailed brightness distribution. And so I'm basically just saying back words, but yeah, that's I can tell you some of the structure of it. This is the guys' names are Doug Hope and Stuart Jeffries at Georgia State and University of Georgia, respectively. I'm sorry, Georgia Tech and Georgia State, respectively. And then there's the team in Rome, Gianluca and others. They have their own deconvolution team, and they're collaborating with them. And so just recently now, this software is called Kraken, and they just a few days ago informed me that they're now able to run Kraken on their supercomputers there in Rome. So that's the team that's working on it, and there's some publications referenced in the paper. So.
Okay, from Jim, he says, great presentation, thank you. Are there any efforts to apply this technology to the larger stellar disks? I think
right, yeah, no, that so I mentioned that earlier. These planet-forming regions, circumstellar disks, particularly in Taurus Auriga. I know AB Auriga is one of the big targets are being used, and they're in particular looking for Lyman alpha. So a lot of the instrument, I'm sorry, H alpha. They're looking for H alpha. So a lot of the design of the instrument, like the dichroic, for example, that picks off the light, makes sure it makes a point of sending the H alpha to SHARK-VIS, and that's the primary science goal, is looking at the larger circumstellar disks.
Okay. From Steve, has the JWST been used on EO, especially in the infrared?
Yeah, so I'm actually on a team, and we got with Imke de Potter leads a gigantic team that got early release science time, and we observed EO with JWST. I think it was in August 22, but we were using a kind of unique instrument on JWST called NIRIS, which uses something called aperture masking. And aperture masking is a technique in which you actually mask off a large portion of your primary mirror to do interferometry. You use little small, you just let light through in 7 or 8 smaller holes. And then it's a standard technique in interferometry. You can actually get higher resolution than you would get, believe it or not, using the whole mirror. And long story short, it just, we didn't get anything earth-shaking, I'm afraid. We're having a lot of trouble. In fact, I'm meeting next week. We're trying to figure out how to get a publication out of it. We're mostly going to be talking about the technique and that's used to analyze the data. We're combining it with some LBT data that we took using that 23 meter mode. But being honest, we got some problems with that data as well. So yeah, we're struggling. But yeah, that's the only observation. Well, I'm sorry. There's been other teams that have used near spec to look at EO, part of the same group. But I don't know of any published results from that yet. So JWST is great, but it's a 6.5 meter mirror. And so you have to take advantage of the strength of JWST, which is that it's it's perfect. It doesn't have any of this point spread function distortion, any of that. The stability, the photometry, is perfectly stable. So far for EO, the results have been kind of mixed, observing it with JWST.
Okay, the next question is from Joe. He's asking if the LBT is on the Mount Graham Observatory tour.
Is it on the Mount Graham Observatory tour?
Yeah.
Yes, absolutely. Yeah, discovery tours. You can visit LBT through those discovery tours of the observatories on Mount Graham. Yeah, there's several a month visitors.
Okay. Also from Doug, were there any stellar sources visible in the broader raw frames? The frames shown seem pretty closely cropped, or is that the whole frame?
No, that's the full frame, I think, is something like on the order of 10 arcseconds square, and EO is roughly 1 arcsecond. So yeah, they're cropped. We didn't have any background stars that were notable that could be used for a PSF measurement. We had to use a nearby star. We went to a nearby star to measure the point spread function.
Okay. And the last question from Joe, also wondering, since you mentioned Rome, does the LBT team work at all with the Vatican Observatory team on Mount Graham?
Well, yeah, we certainly know each other and collaborate. There is one very interesting connection between LBT and the Vatican, which is LBT has a completely different type of instrument called PEPSI, which is a super high resolution visible spectrograph with resolution exceeding 100,000, and it's got a couple of unique, in addition to the 2 primary mirrors of LBT, which is the main source, it's got a fiber connection to the Vatican. So there's a fiber, running all the way to the Vatican, which the Vatican is, more available. There's more time available on the Vatican. So it has been commonly used. The Vatican's been used to actually feed light to an instrument that's on the LBT.
Are there any other questions left in the room? Anyone that we did not get their question? Okay, thank you. Well, Dr. Conrad, thank you so very much. This is really a fascinating presentation, and I'm afraid that we assume with our guest speakers that when they come and they get us interested in their research, that they've made a future commitment to come back again and update us when they have some further results. So, I hope that you will be able to do that and come back and visit with us again and help us learn some more fascinating things.
Thank you very much. It'd be my pleasure to come back and
Wonderful. Thank you so
and yeah, Doug, let's catch up.
Okay, thank you so much.
Okay. Thank you very much. I'm going to leave the Zoom.
Okay, good night.
Good night.
Now I think we're going to move to Doug Smith. I think Doug has some AL awards that he wants to give tonight.
So during the last 3 months, because we've had nothing but Zoom meetings here, we've kind of got a backlog of Astronomical League awards. Now, I have a lengthy list here of some awards that have been given out to some of our members. They're not in the room, and some of these awards were mailed directly to the member, but I thought I'd announce them anyway. We've had some busy people during this period. Greg Ruppel, who probably you all know because he always has images in the bulletin and he's very much involved with the imaging. He earned 4 different Astronomical League imaging awards during that 3-month period. He picked up the imaging award for 2 in the View, the imaging award for, let me read it, Bright Nebula, the imaging award for the imaging all the Messier objects, and the imaging award for the open clusters. Picked them all up during the last 3 months. We also had, I think, our first Herschel II recipient, Kevin Mayak, picked up his Herschel II. Bill Clark, who's gotten a lot of awards in the past, he picked up 2 more Citizen Science Awards during that period. And then we've got 2 awards to give out to somebody who's in the room. Pete Herms. Come on up. So Pete Herms, okay. He picked up his Binocular Double Star Award. And more interesting, at least from my standpoint, he got his Binocular Master Observer Certificate. And he's one of the very first people to do that. This is a fairly new award that was just put together in the last year in the Astronomical League. And he's one of the first ones to get it. He's the first one in TAAA to get it. So, what does he? I don't know. And he gets 2 nice pins to go with it. So congratulations, Pete.
Okay, we do not have Dr. Kokoschka with us tonight, so the planet report for the month will not be given in person. But if you look at our website at TucsonAstronomy.org, planet report for each month is posted there, and so he will have posted it there for you, and you can read it and check it anytime during the month. And I wanted to also check to see if we have any new members with us tonight, either in person or online. If we have any. Okay, do you want to introduce yourself to us? Okay, so we have a person who's not joined yet, but who is new. This is his first time.
Matthew Benet. No, the Zoom people for their sake. Yeah, okay. My name is Matthew Benet. Despite appearances, I am an astronomer. I'm working on a project for a radar that will search for and detect dangerous asteroids. It's actually very feasible. I have some cards here with my info if you want to have a look at it, and it'll steer you to my my YouTube channel with the relevant playlist. So it's a feasible thing to do. Byproduct of this is using the same type of technology as in the SETI problem, which would be far better than it's being done now by other people. So if you know, if you have some time to waste, or you know, you're tired of Flintstone videos on YouTube, you could try some of these. And then I might become a regular member. Oh, also, if you know anyone who would like to support this work, that'd be fine. And if you know someone who needs an employee with a trainable IQ, then I'm up for that too. Anybody wants any cards?
Okay, thank you so much. Okay, we appreciate everyone coming tonight. And Terry was very helpful to remind me of an interesting piece of information, that this particular room that we're meeting in, the 204 room that we're meeting in Stewart Observatory tonight, was where we started meeting, I think in 1956, was it? 1954. So it's like home night for us to be meeting in this room tonight. Okay. So, it was, somebody made a comment and I didn't hear what the comment was. It's much better? Okay. Okay. Well, thank you everyone for coming tonight. We've enjoyed having you. And there is going to be a social hour after this for people who want to come at the IHOP. And it's going to be the IHOP that's which one, Terry?
22nd Street and Columbus, maybe? Is that it? So west of Columbus, east of Alvernon.
Okay. Wonderful. So thank you, everyone, and we will talk to you all soon. So good night and have a good evening. The next meeting will be in the regular room. Yes. No, we won't. Okay.
So it's supposed to be in this room. But when we were over there gathering the camera and everything, they had the new projector screen sitting out on the floor. So maybe if they get it done in the next few weeks, maybe we can go over there. I'll let you, it'll be in the newsletter though. Okay.
We will clearly announce to everyone and send out the emails about where the next meeting is going to be for sure, but it will be in Stewart Observatory, the same building as usual, and either the room that we have tonight or the room that we normally have. So, okay, so thank you everyone. Good night and have a good evening.